When electron absorbs energy, it moves from one energy level to uh, one energy level to an higher energy level. But electron can absorb one photon at a time, one photon. Number two, electron can only absorb a photon that can make it move from one energy level to another energy level. It cannot go a bit beyond energy level or before energy level. It has to have the exact same energy to move from one energy level to another energy level. Secondly, this shift of electron from one energy level to another energy level is instantaneous. And over here, this word has more specific meaning. Electron does not consume any time to go from one energy level to another energy level. It is not actually going from one energy level to another energy level. It is like disappearing from one energy level and appearing in another energy level at the same time. There's no delay between these two. And it is not like one more thing that we need to understand, that it is like it's not that physically electron is going from one energy level to another energy level. It is that um, it is not a physical level in space. It is a kind of energy that electron did not have that energy, and now electron has that energy. And because it is happening by absorbing a photon, so there is no gradual process of electron gaining that energy. For example, you can say that electron has an energy of 1, and now it has an energy of 3. It was not like energy became 1.1, 1.2, 1.3, 1.4, 2, 2.5, 2.8, 2.9, and then 3. No, it was 1, and now it is 3. That energy changed to another energy level. Electrons' energy changed from one energy to another energy without consuming any time. Now, this is a cold gas over here. We have a sample of cold gas. And this is a beam of assorted photons. One example is sunlight. Sunlight has all the possible photons that can be there, especially sun at daytime. Because in the morning and near the morning, near the evening, specific frequencies can only reach us. And this is why many people believe that sun is yellow, because when sun is of the color that we can see, like mostly we can see sun when it is morning or evening. At that time, sun is red or yellow. But actually, the sunlight is more white. And if you want to check the color of sun, you have to see it at daytime, like at noon. When you see sun at noon, you find that its light will be more white. Now, white light is passing through the cold gas, and what we get over here is different. Like this light, which is the sunlight, is this continuous spectrum. The light that we get after the gas is this. You can see that some lines are missing. These lines are missing. So these lines got absorbed by the cold gas. So the problem is that why exactly these lines are absorbed? Because if it is a pure gas, electrons only have specific jumps that they can make. They can only have specific, they can only absorb specific photons. So only those absorbed photons are missing. And this is how we can find out if we have a pure gas and we want to check what gas is this. This can be a signature of a gas. We can pass light through it and see which frequencies it absorbs, and on the basis of that, we can find out what gas we are dealing with. So this is a way of finding which gas is this in physics, like without doing those chemical reactions and seeing the flame color or flame test or anything. This is how we can check which gas is this by passing a beam of white light. Now, here is a question. A very favorite question of examiner. State what is meant by photon. Answer is a photon is a discrete packet of electromagnetic energy. Some people say it is a quantum packet, the same word, no differences. A light beam has a continuous spectrum. By continuous spectrum, we mean that it has all the frequencies within the visible region. The photons of light have energies ranging from 1.6 electrovolt to 2.6 electrovolt. So minimum energy is 1.6 and maximum energy is 2.6. And all that is within the part of human visibility range. The beam passes through through some hydrogen gas. It then passes through a different grating, a diffraction grating, and an absorption spectrum is observed. All the light absorbed by the hydrogen is re-emitted. Explain why dark lines are still observed in the absorption spectrum. This is a very good question. Question is, if this is the cold gas and it absorbs energy, we know that energy which has been absorbed is also emitted out. So if gas is emitting that energy, which it absorbing, then why we like some of the energy must be released in the same direction as we are observing. So we should have some light over here. So there should not be these dark lines. But the difference, which is very important to understand. The difference is that light ray that gets on these dark lines is not as intense as the rest of the lines are. So here's an answer. Gas emits absorbed light in all directions radially. This would be an enough answer, but if you want to show off to the examiner, you can say intensity of light at dark lines is very low. Some of the energy levels of an electron in an hydrogen atom are illustrated over here. Hydrogen is an easier atom. So electrons have very small range of energy levels. Now we have minus 13.6, minus 3.4, minus 1.5, all these energies. The question is, dark lines in the absorption spectrum are the result of electron transition between energy levels. On figure 10.1, draw arrows to show the initial electron transition between the energy levels that could rise to the dark lines in the absorption spectrum. Now remember we have energies of 1.6 to 2.6. So do we have energy that can produce this? You have to shift something from 13.6 to 3.4. So you need a photon of 10.2. Do you have 10.2 over here? Remember, we have from 1.6 to 2.6. So no, this is not possible. So this jump is not possible. Now look over here. Is this a possibility? 3.4 minus 1.5. That is 2.89, I guess.
1.8.
Is it 2.89?
1.
So do we have 2.89?
So it's 1.89.
Okay, 1.89. Oh,
G.
1.8. 1.8. That is a possibility. So yes. So this can happen. 3.4 minus 0.85.
2.55.
2.55. So that is also possible. Now 3.4 minus 0.54. 3.4 minus, you can just ignore the minus sign over here because uh, when you will be subtracting, you will have a high energy level minus low energy level. So the minus signs will fix themselves. Just ignore the minus level energy levels over here. There's not minus sign. 3.4 minus 0.54 will be
2.86.
Okay, 2.86 is not possible because we have only from 1.6 to 2.6. Now 1.5 minus 0.85.
0.66. Not possible.
Okay, we don't have that as well because the lowest one we have is 1.6. So yes, only these two are the possibilities in the given range of the spectrum. So that's why we have 2 marks over here. Calculate the shortest wavelength of the light in the beam. Now, shortest wavelength. Now, what do you think shortest wavelength will belong to? Will it belong to 1.6 electrovolt or 2.6 electrovolt? What do you think? Will shortest wavelength will belong to 1.6? Remember, when you say shortest wavelength, you're actually saying highest frequency. When you're saying highest frequency, E equals to HF reminds you you're talking about more energy. So calculate the shortest wavelength of the beam in the light. Which photon you think will have the shortest wavelength, 1.6 or 2.6?
1.6.
No, it will be 2.6. 2.6 has more energy, so it has more frequency. When it has more frequency, it has shorter wavelength. So 2.6 electrovolt. First step, convert electrovolt into joule. Second, use E equals to HF to find F. 3, use C equals to F lambda to find lambda. Okay, 3-step calculation. I'm giving you 3 minutes to do it. Hurry up. Let's see if your answer is 4.8. Let me check it. 2.6 into 1.6 into 10 to the power minus 19 joule of energy equals to H into F. So F will be this divided by Planck constant, which is 6.63 into 10 to the power minus 34. Did I put the value right for the Planck constant?
Yes, sir.
Sir, I think
So
I got 4.7 into 10 to power minus 7.
is it 4.7 or 4.78?
4.78.
So why it is 4.7 then if it is 4.78?
Sorry, 4.8, I think. 4.8 into 10 to power minus 7.
Good, good. So frequency will be all this speed of light divided by this. So C multiplied by C is 3.0 into 10 to the power 8 multiplied by 6.63 into 10 to the power minus 34 whole divided by 2.6 into 1.6 into 10 to the power minus 19. Just pick calculator once, put everything in, you should get
Yeah, sir.
minus 7. It is 480 nanometers, which seems like blue color light. Okay. The band theory is banned. We don't do band theory anymore. It is removed from the quantum.
Excuse me, sir.
Yes.
Sir, I had a problem in one question. Like,
Okay. Here's a question. Figure 9.1 shows a visible part of emission spectrum of hydrogen gas in a laboratory. The number of the numbers indicate the wavelengths in nanometer represented in each. So these wavelengths are missing. Hydrogen. Explain how the emission spectrum provides evidence for existence of discrete energy levels for electrons. Only certain wavelengths are missing from continuous spectrum. Only certain wavelengths are missing over there. This is because electrons only absorb one photon at a time of selected energy. So only certain energies got absorbed and produced absorption line spectrum. Now, energy levels in hydrogens are given 3.4. Okay, some of the energy levels show that the energy level X is 1 minus 1.5. The wavelength of the radiation in figure this relates to minus 3.4 electrovolt. Shows 5 of the energy levels in the hydrogen atom. The wavelengths of the radiation shown in figure this. Okay, all these wavelengths are over here. 3 marks. This is the shortest wavelength I can see, okay? And this jump, which is a possibility, and this will definitely happen, it relates to max energy max frequency, smallest wavelength. So smallest wavelength was 411 nanometer. Can you use this nanometer to find energy in electrovolts? Energy equals to Hc over lambda. And if you energy in electrovolt will be 6.63 into 10 to the power minus 34 into 3.0 into 10 to the power 8 divided by 411 into 10 to the power minus 9 and 1.6 into 10 to the power minus 19. Just put everything in calculator and share answer.
Three 3.024.
3.0.
24.
Why it cannot be correct?
I got 302.
Just 1 second.
Lower energy. Hello.
Hello, sir.
Hello.
जी आप कुछ कह रहे थे?
Actually, I've been talking for a long time, but I recently knew that I was mute. I repeated many times that just put it in a calculator and show me the answer, and I made a mistake somewhere. Did you get the part when I said I made a mistake?
No, sir.
Oh, actually, I just realized that I have made this mistake that actually this is the shortest energy gap. So shortest energy gap relates to lowest energy, relates to lowest frequency and largest wavelength. So I don't know why I related to maximum energy. So
It's fine.
actually, it was the shortest wavelength. So it means that an energy of this much electrovolt has been absorbed, and to make this energy absorption, X has to be minus 1.51 electrovolt. Now, the same part of emission spectrum from hydrogen is observed light from a star in a distant galaxy. The number indicated is this. The spectrum shown different wavelengths. State the name of phenomena that gives rise to change in wavelength. Doppler's effect. Oops. Okay, this part is Doppler's effect. State the phenomenon shown about the motion of galaxy. Because the wavelength is increasing, it means that the galaxy is moving away. Use this to correspond, determine the speed of the distant galaxy. We haven't done it yet. This is astrophysics, but you can do change in wavelength divided by wavelength equals to speed over speed of light. But we will be doing it in the later classes. Right now, we haven't done this topic. Okay. I will be writing formulas over there that won't make sense to you, so there's no point of doing it right now. We can do it when do these two last parts with astrophysics. Okay, that's end for today. See you people in next class tomorrow.
Okay, sir.